Let's get started. So we're starting a new learning objective today, functional programming and concurrency. The next homework is out. The grader's not released yet. I'll have the grader at the latest, probably Thursday. But the next homework is posted. Yeah? Yep. For project 2, no. So including testing, those are banned. For point of sale, yeah, not in testing, including your testing. And that's mostly, it's mostly because if I don't have that, students could hide conditionals in the testing code, and I wouldn't have a great way to check that. So unfortunately, I have to ban it. I just look at all of your code, and if there's any conditionals, I just don't compile it. Yes? Can you use what? Yes. Yeah, you can use double equals. Not when you're comparing doubles, of course, but when you're comparing two values, you can still use double equals. So your asserts are still checking if a Boolean condition is true or false, but it's not running your code conditionally. So that's the difference. As long as code that you wrote isn't being ran conditionally, you can call code that runs code conditionally, which is like an assert statement. You wouldn't be able to assert anything in your testing if I didn't allow that. We are on the next one, genetic algorithm. I'll just give a very brief introduction to this one. So a genetic algorithm, the way I like to explain it is it's a glorified guess and check program. We're going to write things super generically and have a genetic algorithm that can solve any optimization problem that we give it, as long as we give it a cost function and an incubator function as inputs, and then it'll keep guessing different genes to put in the incubator, create what we call animals, to use some of the terminology, and then test those animals based on the fitness function, keep the most fit animals for the next generation, and keep going until we find a really optimal solution to the problem. The genetic algorithm doesn't know anything about the problems, it just knows how to optimize based on the cost function. So that's what we want to do. Similar to the last homework where we had a restriction, we do have a restriction on this one too, and it's a big one. Var is banned. No variables for homework 3. No variables. Nothing else is banned except variables. You can use val still. So you can still store values and use those values in your code, but you can't have a value that's changing. So you can't have a variable, and you can't have any mutable state throughout your program. So if you say, well, I'm going to have a mutable list, I'm going to import that and then just use that as a big old variable, but use it as a val. That's also banned. Anything that changes state, not going to be allowed. So how do we do that? And similar to the second project, I do this to force you to use functional programming. We're going to learn all about functional programming. But if you can use var, you can just avoid all functional programming. Banning var, this is my way of saying, no, you're going to learn functional programming. You might not like it. You might not like functional programming. But at the very least, coming out of this class, you're going to know what functional programming really is and how it feels to code using functional programming. Then after this class, if you don't want to use it again, whatever. But I'm exposing you to OOP and FP. You're going to have both of those in your programming toolbox by the time you leave this class. So this is my way of forcing it. There's nothing wrong with variables, but functional programming really doesn't like state. The word I use like 100 times over the past 3 weeks, functional programming says, you know what, that whole state thing? Nah, none of that. No changing state at all. That's a fundamental idea of functional programming. So we're going to ban state and write our code with that restriction. We're going to start by talking about sorting. We've talked about sorting quite a few times in 115. We talked about it once in 116. We're going to visit again this lecture and on Wednesday's lecture. Project 4 restriction, no functions. Sup, Dragos. Project 4, there are no restrictions. All restrictions are lifted. So in LO2, I need to force you to use OOP. In LO3, I need to force you to use functional programming. For LO4, where you're using data structures and algorithms, there's no restrictions. It's up to you what to use after that. If you think creating a bunch of classes with changing state is going to make your life easier, go for it. If you think creating a whole bunch of first-order functions and higher-order functions, go for that too. It's up to you after that. But in the middle two learning objectives of the course, I want you to be exposed to two different paradigms of programming other than procedural programming, which is what we do in 115, just writing procedures and calling those procedures. We usually call them functions, and writing like that. So let's learn about functional programming. We won't be able to get far enough in one lecture. There's quite a bit of stuff that I need to lay the foundation for functional programming. So there's not enough in this lecture to even get to lecture task 1. So lecture task 1 I'll introduce on Wednesday. So today, no lecture question attached to this lecture, just because you won't be able to get to the first one yet. There's a few other things that we need before we get there. But let's talk about first-order functions, or first-class functions, as they're usually called. I call them first-order functions in this class, but I think first-class functions is a more common terminology. And we're going to talk about it in terms of sorting. I assume you all know how to sort. I'll give some review on sorting, but I'm using sorting as a way to leverage functional programming, to introduce functional programming. I want to start with something that you're already familiar with, and then add another layer of understanding on top of sorting. And I'll give you a little bit of warning, foreshadow, whatever. You're going to see sorting multiple more times throughout your career. If you're going through the whole CSE curriculum, you're going to see sorting again in 250, where it's used to show you how to analyze runtime of an algorithm. You're going to see merge sort on Wednesday. You're going to see merge sort again in 250. I'm going to show you merge sort to talk about first order functions some more and functional programming. In 250, you're going to talk about merge sort and learn how to analyze the runtime of merge sort. And in 331, you're going to see merge sort again, where you learn how to prove that an algorithm is correct on all possible inputs. So you'll see sorting a lot, but each time we introduce sorting, I'm going to turn this volume down. Each time we introduce sorting, each time we revisit sorting, we're leveraging sorting, your understanding of sorting, to show you a new concept. So when you get to 250 and 331, you'll be tempted to be like, oh, merge sort again? I'm going to turn off my brain and not pay attention to this lecture. We know you already know merge sort. We'll review it so you can see it again. But we're teaching you that new concept by leveraging something you already know. So just a heads up on that, because I thought that was weird as a student. Like, why am I learning merge sort for the 4th time? Like, I get it. I get it already. But now I see like why we do that. We love using sorting as a vehicle to teach you new things. I don't know. We just love sorting in computer science. So we use that as the vehicle to show you new concepts. So sorting. And by the way, I don't expect you to understand merge sort yet, but we'll cover it Wednesday, and I'll really show you how merge sort works. We cover it very, very briefly in 115, if they even still do in 115. It goes by in like half a lecture, I believe. It's like, here's merge sort. Isn't that cool? N log n. And that's about all we do in 115. So we'll go a little more in depth on Wednesday. So sorting, we saw how to sort already in a very limited way. Whenever we had to compare two lists in our testing, and we wanted to check if those two lists had all the same values, but we didn't care about the order of those values. We used .sorted for that, and we would compare sorted copies of each of those lists. .sorted returns a new list with all the same values, but in sorted order. So we called .sorted on both lists, used equal to compare them as long as they didn't contain doubles, which I was careful not to give you a list of doubles for the earlier homeworks. We used equals that compared each value in step at each index, and we did that to be able to tell if two lists contained all the same values in any order. So that was cool, but we didn't have much control here. We just called .sorted and we got what we got. So .sorted is going to use the default comparator for that type. For integers, the default comparator is the less than function, which means we're going to get our values in increasing order. So if we want to sort this list, the minimum value is first, and then increasing, or rather non-decreasing after that. And specifically, if two elements are being compared, and one of them is strictly less than the other one, then it has to come before that other element in the full sorted order. So what if we want a little more flexibility than that? Well, Scala has another method, the sort by method, which is going to take another way to compare the values. This is very similar, so it should feel reminiscent to how we sorted in Python in 115, where you set the key and then sorted by that key. We're doing something very similar here. We're going to give sort by a method in this case, and then sort by the outputs of that method or function, as we'll see in a little bit. We want to finally move away from strictly methods, talk about functions and the difference between them. So a method is attached to a class, or an object rather, is the big difference. So here I'm given the math.abs method to sort by, and we're going to get these values sorted by their absolute values in increasing order. So in increasing order of their absolute values. So 4 has the lowest absolute value, it's first, and then increasing from there. So what we did right there was pass a method as an argument to another method. And yes, we can do that, and it's a magical, glorious world. We're going to do this a lot over the next few weeks. This is kind of the essence of functional programming, this idea that functions are first-class citizens, which means we can treat them as any other type in our code. We can use them as arguments, we can store them as variables, we can even return, we can have methods that return functions and use those functions as inputs to other methods. We can move functions around just like we can any other value, like an int or a list. We can do that with functions as well. That's the core of what we're going to talk about for the next few weeks. So this gives us a bit more flexibility, but we still had to use the default ordering. So math.abs returned an int, and then we just used the default method of sorting on ints, just increasing order. So we would like more flexibility than this. So we're going to look at the next thing, sort with, and this is going to be more reminiscent of how we sorted in JavaScript in 115, where we gave the sorting method a comparator and then sorted by that comparator. And this gives us the most flexibility we can do. There's no limit to what we can sort when we're sorting with comparators like this. So we're going to define a comparator for our data structure, for our list in this case, that's going to sort based on the output of this comparator. The comparator is going to take 2 inputs of the type of the data to be sorted and return a Boolean. It's going to return true if the first value should come before the second value and false otherwise, including ties. So if they're tied, it'll return false. With a comparator like this gives us all of the information we need to be able to sort any data structure of elements that we want to sort. So I have a comparator that takes 2 ints and returns the first int greater than the second int. This is going to give me decreasing sorting. Instead of the default less than, I'm going to change that to greater than and get decreasing order. So if A should come before B, this will be true, because as long as A is greater than B, then A comes before B. If they're tied, this will return false, and if B is larger, this will return false. But if A is strictly greater than B, A comes before B in the overall ordering, the sorted ordering. So this is a first order function or a first class function. This is what we want to talk about for the next few weeks. So we created a function by specifying a parameter list, just like we did with methods. The syntax is completely the same. We have a parameter list in parentheses, but we didn't give this function a name. This is what we call an anonymous function. It doesn't have a name. We just gave a parameter list, and then instead of just the equal sign, we have Scala dev's favorite, a big arrow. We have equal sign greater than. This is our arrow, which for a method you would just have the equal sign. For functions, we're going to have a big arrow and then the definition of the function. What should be returned? This function is only one statement, so the last statement that's executed when this function runs is always going to be this line, which returns a Boolean. So I have a function that takes 2 ints and returns a Boolean, and I'm giving that as the input to the sort with method. So I'm going to sort based on this comparator, and I'm going to sort all the values in the list based on the return values of this comparator whenever 2 values are being compared. And that's all we need to sort. We'll see an example in a bit. But that's all we need to sort anything is just the comparator. We did this in JavaScript in 1.15, if you took it here. And we want to explore why this works, how would we write our own sort with method, and just overall what's going on with the sorting. So we can split this up a little bit just to see fully what's going on. I'm going to instead store my function in a variable and then call sort with like we were before. And I'm going to create my function using the same syntax as before. So I'm doing the same thing, but I want to split this up a little bit to show you how these functions are being stored in our program. When we're moving away from methods and moving to functions, how do they behave, and how can we work with them? So we have our function, the definition exactly the same as the previous slide. But instead of defining this directly in the call of sort with, I'm storing it in a variable, or value in this case. I'm storing it in a value, and then passing that value in as the parameter. So the important thing here is that when we create a value or a variable of a type of a function, the type of that variable or value isn't just type function, it's a type that specifies the inputs and the output types. So I have a variable, a value here named comparator, of type function of int and int to Boolean. I'm going to use similar syntax to what I did on the right side of this assignment. I have the parameter list with just the types, big arrow, and then return type. So I'm specifying only the types. And now this value has to store a function that takes 2 ints and returns a Boolean. I have the equal. This is why we can't use equal right here, because equal already means something here. It's the assignment operator. So the assignment operator, just like we would, like if this said val x of type int equals 7, that equal is doing the same thing. It's assigning a value to a value, I'll call it a variable, even though we use val here. Assigning a value to a variable. So we have the assignment operator, and then the value that's going to be stored in that variable, which is this function that returns a greater than b. So this is new syntax we're going to get used to looking at. So I'll let that settle for a second at least. Yeah, where does sort with get A and B? That is a good question, Dragos. It's a good question. You're not going to answer the question. No, I'm not. No, I'm going to answer that question in a few. I have like half this slide deck is all about answering that question. What do we do? So we have this comparator, and we have a whole list. We have, we could have 500 elements in this list. We have a comparator that only compares 2 of them. How the hell does that help us? That's what I'll spend a bit of time answering. Right now, I want to absorb the syntax of a function. The type of a variable for a function or a parameter, like this sort with method, takes a parameter of type int and int to Boolean, assuming that this is a list of integers. Whatever the type of this list is, I didn't specify my type explicitly here, but whatever type this list is, then this comparator has to take 2 of those and return a Boolean. So if this is a list of doubles, take 2 doubles and return a Boolean. If it's a list of strings, 2 strings and returns a Boolean. If it's a list of maps of strings to doubles, then it's got to take 2 lists of maps of strings to doubles and return a Boolean. It has to match the type parameter of the data structure that we're sorting. This is a list of ints, so we'll give it a comparator of 2 ints. You're not really sure when to explicitly type your variables and values, to be honest. I like to do it always in my lecture slides. I missed one here, obviously. I like to do it always in my lecture slides just to make it 100% clear what my examples are doing, what the types of my variables and my examples are doing. In your code, most of the time you can skip the explicit type parameters for variables. Sometimes that does trip you up. Like here, I don't have to do anything because I'm creating a list, I'm giving it ints. So Scala will infer that this is of type list of int. But there is a chance that Scala will infer that I meant to do a list of longs, for example. And if I want it, I am going to get a list of ints here. But if I want a list of longs, I have to explicitly say, this. No, make this a list of longs. And then it'll convert all the ints to longs. I could skip this as well, because Scala will look at this and say, well, you gave me a function that takes 2 ints and resolves to a Boolean. So Scala will infer that as well. So if you don't have this type here, you'll get away with that as well. Where you absolutely need to specify your types is when it's the parameters to a method or a function. So if I don't specify these as ints, or in any method that we wrote, if we don't specify those types, then we're going to get compiler errors. But for our values and our variables, most of the time Scala can figure it out. But if you do that, you are relying on Scala a bit too much for certain applications, but most of the time you'll get away with it. I just like doing it in my lecture slides to be clear, just for clarity. So first order functions are values, and the value is a Boolean. The value is the entire function. And then that function returns a Boolean in this case. But the type of the function is this entire type, of type function that takes 2 ints and a Boolean in this case. So any method that takes a function that takes 2 ints and returns a Boolean, I can use this as an argument for that method. Yeah. I mean, you should, just to, it's good practice to, but you could get away without it. Like Scala will figure it out what you mean if you don't have that. In most cases. In some cases it won't. And then, IntelliJ will yell at you in those cases. But if you just deleted this part, technically you'd get away with that. But if you're not adding that part because you're not sure what type your function is, I got to question why you don't want to specify your types. If it's just because you don't feel like typing that, that's fine. But if it's because you don't know what to type there, then, so it all depends on what your situation is for my specific answer there. And for functions, you can use the brace syntax, just like we do with methods. You can use this syntax especially if you have a function that's going to be more than one line of code. You can still use that syntax for the body of it instead of just writing it inline like we did. You want more space? Add braces and put the whole body of the function here. I left it as just one line here, but we could have as many lines as we want. Do as much processing as you need to do for your functions. And finally, I got ahead of my slides a little bit, but the type of the function is the type of the parameters and the return type, all specified. And functions are just values. All values in Scala are objects. Functions are just objects. They can be parameters, they can be return values, return types, variables of these types. We can do with functions and even methods everything that we can do with an int or a list or any class that you've defined. These are all just types. They're all objects. And we can do anything with them. This is one of the one thing that in programming that gives us so much power is everything's treated the same like that. And we can, if you can think of something like, I don't know where I'm going with this example, but it's cool. We can pass functions around like this. It's really handy, and it gives us a lot more power, a lot more flexibility in the code we write. So that gets us most of the way there. Let's talk about one more thing, one more step for for comparators is comparing our custom types. So say we have a type animal that we defined. I don't have the full definition of the animal class on the slide, just for brevity here, so it fits on the slide. But what if we have our animal class? These animals have names, and we have some polymorphism. We have an animal class, and we have dog and cat extending animals. So say we have a whole bunch of goodness going on. We have fairly complex behavior, and we want to sort these things by their names while ignoring case. Say that's the use case that we have. We can write a method in this case. It could be a function as well, but we can use methods, is my point. Takes two animals and returns a Boolean, and compares them in increasing order alphabetically, ignoring case. So Morris has a lowercase m, Finn, Snoopy, Garfield have uppercase letters. If we just sort by the default values, it's going to be sorted by the ASCII values of these characters, meaning all lowercase letters come after every uppercase letter. So Morris would be last in the list if we just use the default string sorting. And we can't even do that because we can't sort animals. How are we going to sort animals? There is no default ordering for a type that we created. We give it a default ordering, but we didn't do that in this case. We're going to give it a comparator and define exactly how animals should be sorted, and then call sort with, give it our method by name, no parentheses. We're not calling the method. We're just giving it the entire method. And then sort with is going to call that method as many times as it needs to be able to sort this list. And there's no stopping you. You can sort anything. Once this is a method, I'll have an example in I think next lecture, maybe Friday. Since this is a method, we can also have it depend on the state of the object from which this method came, where this method's defined. So we can actually have this depend on some state. It can be immutable state, as we'll see. Obviously, for the homework, it has to be immutable, but can depend on some state of that object, the state variables. So we can have extra information aside from the inputs of the method. We can also have state variables here that help us compare these things in ways we could only dream of before. We can sort any way we want. Any way you want to sort things, there's just no stopping you. The future is so bright. You can just sort. All right, how does it work, though? So let's talk about this. Let me catch up with Chad a little. Yeah, Dragos, that's what I'll get into that. Yeah, let's get into how this works. So let's talk about selection sort. You saw selection sort at least briefly in 115. You're going to see it just briefly again here. I don't have too much to say about selection sort. I don't think it's too complicated, but I want to focus on its use of a comparator is the main focus right now. So say we have this list, and we want to sort. We're going to sort using the default ordering. So we're going to use the less than comparator and compare all the values to get this expected output. This is what we want outputted. But all we have is the ability to sort two elements at a time. So our selection sort algorithm has to work off of the comparator and only use the comparator to figure out how to order elements. So we're going to compare two elements, just two at a time, and decide how to sort things. So the way selection sort works is we're going to go to each index in the list and figure out which value should go at that index. So we start with the first index, and we're going to compare it with each other index and keep track of the minimum that we find. So we're going to take 5, compare it to 23, and say between 5 and 23, which one comes first? That's a question we're going to ask our comparator. We don't care what the comparator does. We don't know what it does. We're just going to ask the comparator, hey, which one of these comes first? If it returns true, we know 5 comes first. If it returns false, we know either it's a tie or negative 23 comes first. We're going to keep track of which one won, which will be negative 23 in this case, And we're going to go to the next index, compare negative 23 and negative 8. Ask our comparator, which one of these two values comes first? That's going to be negative 23 will win. Then compare the next value, negative 23 and 7. Ask our comparator, which one of these two comes first? It's going to be negative 23. Negative 23 and negative 4, which one comes first? Negative 23 wins. Negative 23 and 10, which one comes first? Our comparator says it's still negative 23. So negative 23 is going to be the winner. That's the value that's going in the first index. It's the minimum value, which we can find, not necessarily minimum value, but the value that comes first according to the comparator that was given. And we can tell that just by asking the comparator two values at a time, which one comes first. So now that we know 23 comes first, we're going to swap 5 and 23. So 23, we know that value comes first. That one's locked in. We never have to look at it ever again because we know that's already in its correct spot. And then we're going to do the same thing with each index. We're going to go to index 1. We're going to say, okay, 5 compare with negative 8. The comparator is going to say negative 8 is going to come first. Or it's a tie. It'll return false, and we'll say, okay, either negative 8 comes first or it's a tie. In either case, we're going to say negative 8 won that battle. Negative 8 and 7, negative 8 wins. Negative 8 and negative 4, negative 8. Negative 8 and 10, negative 8 wins. The comparator says negative 8 is the next value, so we swap these two. Negative 8's locked in. 5 and 7, we're going to ask our comparator which one comes first of these two. Comparator says 5. 5 and negative 4, which one comes first? Comparator says negative 4. Negative 4 and 10, which one comes first? Negative 4, swap. So these ones are locked in. I hope you get the idea by now. I don't want to go through the whole thing. But we're going to keep going index by index, go through all of the remaining unsorted elements, ask the comparator pairwise decisions to make, and then whichever one is the minimum based on those decisions, that's what we're going to take. This is similar to finding the min, that pattern that we saw in 115 that you used again in 116, of taking a list of elements and finding the min. How do I find the closest city with all of these cities, this list of over 100,000 cities? How do I find the closest one? Well, you compare them two at a time and keep track of the closest one that you found so far. But you only ever compare two cities at a time. We're doing the same thing here. We're using a comparator and only comparing two values at a time to find our total ordering using this selection sort algorithm. And here's what it looks like in code. Don't worry, I do have a version in the repo of this that doesn't use var. I think this one's a little more readable just for the slide, but I get that comment every semester. Why did you use var, but you won't let us use it? There is a version in the repo, just because I heard that complaint so many times. I'm like, fine, I'll write a version that doesn't use var, which is fair. I should. But for this one, this is what the code would look like to take what we saw in the previous two slides and put it in code. I have a selection sort method that takes a list of ints and a comparator that takes two ints and returns a Boolean, and it's going to return a list of ints that are the input list of ints, but in sorted order according to that comparator. I don't know what that comparator does. I don't know how it compares to ints. I just know if I give it two values and it returns true, the first value I gave it comes before the second one, and false otherwise. That's all I know about this comparator. I'm going to go through the algorithm. I'm going to iterate through all the indices in the list. And for each one, I'm going to track the min value that I found and then swap the values based on the min that I found. And the big piece of code is right here, taking this comparator, which is a function that takes two ints or a Boolean and returns a Boolean, and use it right here. So nowhere in this function do I ever specify how things are sorted. I just have a very generic algorithm that says, give me a list and a comparator, and I'll return things in sorted order using this selection sort algorithm. So this is where all the decision making happens. If this returns true, I know current value comes before min found. And in that case, current value is my new min found. That's the new smallest element, and that's the new candidate for whatever index I'm currently considering. That's it. I'm just going to call that function. So now this method, this sorting method, can be used no matter how people want to compare ints, no matter how people want to sort ints. So when the Scala developers wrote sort with, like that thing can sort our animal class, which the Scala devs never knew about. They never knew we were going to write that, and if they did, they don't know how we were going to write it. They don't know that we want sorting by name, ignoring case. They don't know any of that stuff. They just wrote a very generic algorithm that can sort anything as long as you give it a comparator, an appropriate comparator. Oh yeah, the sound of sorting is I strongly recommend that YouTube video. It was just posted in lecture. All right, but there's one problem here, and this is how we would use it. There's one problem here is int selection sort, this method I just wrote, only works for ints. It's not going to sort our animals. It's not going to sort anything else other than ints. It's not even going to sort doubles or strings or whatever. So let's fix this. We would like to use this that we used, that we did with the Scala built-in sorting. We'd like to be able to do this same thing. How are we going to accomplish that? And for that, we're going to introduce type parameters. We're going to take another parameter, which is a type. Now, we've seen these before on the other end. We use list and map, which take type parameters. But now it's our turn to write code that's going to take type parameters instead of giving other code type parameters. So instead of hard coding this to ints, we're going to take a type parameter. The type parameter list, and you can have more than one type parameter, is going to be an extra parameter list that comes before the parameter list. So before the parenthesis parameter list, you're going to have a bracket parameter list, which takes a list of types. And type here is a variable name. You can choose whatever you want for that variable. This is saying I work with any type. This method works for any type ever. But whoever's calling this method has to tell me which type they want to use it for. And this gives us tremendous flexibility. So we're going to specify the type when this method is called, so this method can work with any type ever, even types that don't even exist yet. And whenever we use this type in our method, we're going to use that type parameter, whatever we named our type parameter, and just use that type wherever we want. Now, we can't access any specific functionality of this type because we don't know what type it is. We have no idea what it is. It could be of type any, it could be of type nothing or null, it could be anything. So we can't access any of the specific functionality of this type. So anything we want to do to this type, we have to take in as parameters. So for our sorting purposes, I would like a list of that type, whatever this type is. I don't know what type it is, but I'm going to just give me a list of whatever type you want, and I'll work with it. But I have no idea what this type is or how it behaves or what its methods, what its state and behavior are. So also give me a comparator that takes two of this type and returns a Boolean. With a list of that type and a comparator for that type, I can do all my sorting stuff that I need. This algorithm is almost entirely unchanged. I just condensed the code a little bit. I took out the white space. I'm going to create a list of that type, of the type parameter, for the list that I'm going to return, and then run the same exact algorithm. The algorithm doesn't change. And now this algorithm can sort any type in any order based on any comparator. We have full flexibility, a completely generic method that we only have to write once, and we can sort anything. There's none we can't sort with this thing. And this is how the standard library sorting methods work. The Scala developers spend a lot of time writing one really, really nice sorting algorithm, have it take type parameters and a comparator, and then they never write sorting again. Sorting is done for that language. For Scala, they write it once, and a few more methods just for our convenience, the sort by, sort with, things like that. But the algorithm, the underlying algorithm, never changes. They write that one time and reuse that code whatever they want to sort, however they want to sort it with, however we want to sort anything, we use that one method. Completely generic, very flexible. And when we use type parameters, we typically use one variable names. It's one case in programming where I'm a fan of single variable names. It's just convention. Typically an uppercase T for the type parameter, except in certain cases for maps, K and V for key and value are common. A and B are very common, but single capital letters for type parameters. It's just the convention, it's the standard. Across languages too. That one really stuck, having single letter uppercase names for our type parameters. For whatever reason, that stuck, so we'll stick with that. But again, this is a variable name. This is something you get to name. You could name it whatever you want. You can name it A, B, C, D. It doesn't matter. It does matter for style, but it doesn't matter for functionality, I should say. And now when we call this method, we can give it a type parameter. We say selection sort, give it the type parameter list, and then the parameter list, the value parameter list. So we're going to call selection sort on our animals, give it our list of animals, give it our comparator of animals. So all these T's for this specific method call, all of these T's are replaced by animal at runtime because the type parameter T is type animal in this case. We could call this again with the type parameter of int, double, string, and whatever we give it as the type parameter, all the T's will effectively be replaced by that type. And we typically don't specify the type parameter explicitly. This is one case where I think it's almost universal where you don't specify the type parameter explicitly whenever you don't need to. So here, Scala we'll use Scala in type inference here. We gave it animals, which is of type list of animals. We gave it animal.compareAnimals, which takes two animals and returns a Boolean. Scala is going to look at this and say, oh, a list of T and two T's, a function that takes two T's and returns a Boolean, and you gave me list of animal, and animal to Boolean. Scala's going to be like, I know what you got going on here. Type parameter is animal. And it's going to fill that in for you. Same thing like it does with these type parameters, but with type parameters like this, it's more common. I rarely see code that actually specifies the type parameter on a method call. When you're creating an object, like a list of ints or something, that's much more common to specify the type parameter in the variable type. But in method calls, typically don't see it. So I'm fine with that if you don't explicitly specify your type parameters on method calls. Isn't selection sort considered inefficient? And why are we learning it? Good question. It's actually my next slide. Selection sort's terrible. Especially the way I implemented it, it's extremely slow. It's terribly inefficient. But it's nice for learning because it fits on a slide and I can explain everything about selection sort in like 2 slides. I showed you everything that selection sort does. On Wednesday, we want to talk about merge sort, which is going to be more efficient, which is close to, at least asymptotically, as efficient as we can get when it comes to sorting. But it's going to take a whole lecture to talk about that one. Today, I introduced selection sort just to introduce functions as parameters, functions as arguments, functions in variables. That's why I'm using selection sort. On Wednesday, I'm going to talk about merge sort. We're going to do all the same stuff. We're going to slap a layer of recursion on top of it and have a lot of fun. If I did recursion in today's lecture, it's just too much. That's why I start off with selection sort. And with that, I'll see you all Wednesday.